Good afternoon and welcome to Purdue. Thank you for giving us this opportunity to present. And so what I'm going to talk about is a very simple device, lateral flow. The charm of lateral flow system is that you have a strip, you drop a sample, the sample flows by capillary reaction, it gets caught at a signal generation point, and the signal comes out. Okay, you can just see it visually. That's the charm of lateral flow. It's very simple. And the market for this is about $4 billion. Okay, so it's used in a range of diagnostics. And so here the application that we are trying to show is in cervical cancer detection. Cervical cancer is the fourth common cancer among women and seventh overall in all cancers. And it's mostly prevalent in the low to middle income countries. And the most common method is so the most common method to detect cervical cancer right now is rushing through is HPV, is human papillomavirus. So basically, it assumes that anybody who has a cervical cancer will have this HPV infection. And the problem with this is that although it is very, very sensitive, the specificity is very low. So what we propose is a suite of biomarkers with a highly sensitive lateral flow device. And so what we're going to show is that we can increase the sensitivity of the lateral flow device beyond almost to a single molecule. Okay. And also we want to make it very simple, right? And the enhanced limit of detection is about femtogram per ml. So this is how it works. So basically, you drop a sample. And the standard system, the sample flows, the signal comes, and then you read out visually. So what we've done is that the problem that is compounding this device is that the efficiency of capture, right? So when you flow, the capture ratio is very, very low. Maybe less than 5% of the target is captured. So that's why the sensitivity is very low. So what we've done is we put a magnet here to slow down the movement of the targets. So we want to capture as many targets as possible here. So that's what we showed you. So by capturing as many targets as possible, we can increase the limit of detection to femtogram level. So the conventional limit of detection is in the nanogram level or sometimes in the picogram. So this is possible by visual readout. So that is pretty much what it is. So we put the magnet, pull the magnet, and then read out. So we've looked at VCP. This is one of the biomarkers for cervical cancer. This has about 95% sensitivity and about 94% specificity. We validated all this, and we could detect this at about 25 femtogram per ml visually. And we've also done this, this in purified proteins. We've also done the same detection in tissue extracts as well, so we could go up to 16 picogram per ml. And also we've extended this technology to look at whole cells of bacteria like E. coli, O157, and so on. So that one we can detect at about 25 CFU per ml. So the conventional lateral flow systems could detect at 10 power 3 to 10 power 4 CFU per ml. So this is about 1,000 to 10,000 kilograms. And yet the device is very, very simple. So basically, we believe that we could take diagnostics, visual diagnostics, to single molecule. And that's pretty good.